When you work in a team on a software project, or even alone with a professional pipeline in mind, the way you organize your branches in Git is not a trivial matter. Branches are not just a convenience for parallel development, they are a critical security boundary. A poorly configured branch policy can allow malicious or accidental code to reach production without review, bypass automated security checks, or permanently erase audit traces that are essential for incident investigation. This chapter explains what secure branch policies are, why they matter in a DevSecOps context, and what concrete rules you should know and apply. Before anything else, what is a branch policy? A branch policy is a set of rules applied to a specific branch in a version control platform such as GitHub, GitLab, or Bitbucket. These rules govern who can push code to a branch, under what conditions a merge is allowed, and what automated checks must pass before integration. Branch policies transform a branch from a simple line of commits into a protected gate that enforces quality and security standards automatically. Without branch policies, any developer with write access to a repository can push directly to any branch, including the main branch or the production branch. This means a single mistake, a malicious insider, or a compromised account can deploy dangerous code to production in seconds, without any review or automated verification. The critical importance of protecting the main branch. In most projects, the main branch, often called main or master, represents the authoritative version of the application. It is the branch from which production deployments are triggered. Because of its central role, it must be the most protected branch in the repository. Protecting the main branch means, at minimum, forbidding direct pushes from anyone, including repository administrators, requiring that all changes arrive via a pull request, also called a merge request in GitLab, requiring that at least one other person reviews and approves the pull request before it can be merged, requiring that all automated pipeline checks pass before merging is allowed. If a developer can push directly to the main branch, the entire pipeline of security checks is bypassed. A secret accidentally included in a commit, a vulnerable dependency, or malicious code introduced by a compromised account could reach production instantly. The protection of the main branch is therefore not an optional best practice, it is a foundational security control. Pull requests and code review as a security layer. A pull request is a formal request to integrate the code from one branch into another. It is not merely a development workflow tool. In a security context, the pull request is the moment when human eyes and automated tools examine a change before it is permanently integrated. Code review by at least one other person serves several security purposes. A reviewer can spot logic errors that introduce vulnerabilities, such as missing authentication checks or incorrect input validation. A reviewer can detect hard-coded secrets, credentials, or sensitive configuration values that should not be committed. A reviewer can flag the introduction of new dependencies that carry known vulnerabilities. A reviewer provides accountability. Changes are not anonymous, they are associated with a named author and a named approver. For maximum effectiveness, the policy should require that the person who authored the code cannot be the person who approves their own pull request. This separation of duties is a classic security principle applied to version control. For example, if a developer named Alice wants to merge a change that modifies the authentication module, the policy should require that at least one other developer, Bob, for instance, reviews and explicitly approves the change. Only after Bob's approval, and after all automated checks pass, can Alice's branch be merged into the main branch. Required status checks, connecting security automation to branch policies. One of the most powerful features of modern branch policies is the ability to block merges until specific automated pipeline jobs have completed successfully. These are called required status checks. In practice, this means you configure your branch protection rules to require that jobs such as the following must all succeed before any pull request can be merged. Static application security testing. Automated tools scan the source code for known vulnerability patterns without executing the application. If the scan finds a critical issue, the merge is blocked. Software composition analysis. Automated tools check all project dependencies, libraries, packages, against databases of known vulnerabilities. If a dependency with a critical vulnerability is introduced, the merge is blocked. Unit tests and integration tests. Functional correctness is verified automatically. A broken build cannot reach production. Secret scanning. Automated tools search the committed code for patterns resembling passwords, tokens, or private keys. A commit containing what looks like an API key is flagged and the merge is blocked. By connecting these automated checks to branch policies, you make it structurally impossible to merge code that has not passed your security gates. This is the core idea of shifting security left, moving security checks as early as possible in the development process, so that vulnerabilities are caught before they reach production. For example, a developer opens a pull request that adds a new open-source library to the project. The software composition analysis job runs automatically, detects that the library has a known critical vulnerability, and reports a failed status check. The branch policy prevents the merge until the developer replaces the library with a safe version and the check passes. Force push protection and history integrity. In the previous workshops and quiz, you explored Git history and traceability. You learned that Git's history is a chain of commits that can serve as an audit trail for security investigations. Branch policies must protect this history from being rewritten. A force push is a Git operation that rewrites the history of a branch on the remote repository, replacing existing commits with new ones. Force pushing to a shared or protected branch is extremely dangerous for several reasons. It destroys audit trail entries. If a malicious commit was force pushed out of history, it may be impossible to prove it ever existed. It can overwrite the work of other developers without warning. It can be used deliberately by a malicious insider to erase evidence of a security incident. Secure branch policies must include a rule that disables force pushes on protected branches. All major platforms support this option. Once enabled, even administrators cannot rewrite the history of the protected branch, preserving the integrity of the audit trail. Deletion protection. Related to force push protection is deletion protection. A branch policy should prevent the deletion of critical branches such as the main branch or long-lived release branches. If a protected branch could be deleted, all its history would become inaccessible, erasing months or years of audit trail. Deletion protection ensures that no one can accidentally or maliciously remove these critical branches. Branch naming conventions and their security relevance. Branch naming conventions may seem like a purely organizational matter, but they have security implications in automated pipelines. Most continuous integration and continuous deployment systems trigger different pipelines depending on the branch name. For example, a branch name starting with feature/may trigger only basic tests. A branch named main or release/may trigger the full security scanning pipeline and deployment to production. If naming conventions are not enforced and documented, a developer might accidentally or deliberately name a branch in a way that triggers the production deployment pipeline from an unreviewed branch. Branch policies on some platforms allow you to restrict which branch names can be created, reducing this risk. Minimum number of reviewers and stale review dismissal. Setting a minimum number of required reviewers is a concrete policy parameter. For sensitive projects or critical branches, requiring 2 or more reviewers increases the likelihood that a vulnerability or a malicious change will be caught. Another important related rule is stale review dismissal. This means that if a pull request receives an approval from a reviewer, but then additional commits are pushed to that pull request branch afterward, the previous approval is automatically invalidated and a new review is required. Without this rule, a developer could get approval for a clean version of their code, then push additional malicious commits after the approval, and merge the modified code without anyone reviewing the final state. Stale review dismissal closes this loophole by ensuring that approvals always apply to the exact current state of the code. For example, Bob approves Alice's pull request after reviewing her changes. Alice then pushes one more commit to the same branch, claiming it is a minor formatting fix. Without stale review dismissal, Alice could merge immediately. With stale review dismissal enabled, Bob's approval is invalidated and he must review and reapprove the updated branch before merging as possible. Code owners and automatic review assignment. Large repositories often contain many modules, each maintained by different teams. A mechanism called code owners allows you to define, in a configuration file, which people or teams are responsible for which parts of the codebase. When a pull request modifies a file that belongs to a defined code owner, the platform automatically requests a review from that code owner and may require their approval before the merge is allowed. From a security perspective, this ensures that critical security-sensitive files, such as authentication modules, cryptographic routines, or pipeline configuration files, always receive review from the people who are most qualified to evaluate changes to them. It prevents a situation where a developer unfamiliar with the security implications of a module approves a dangerous change to it. For example, a code owner's file specifies that any change to the file auth/login.py requires approval from the security team. When a developer opens a pull request modifying that file, the security team is automatically added as required reviewers, and their approval is mandatory before the merge can proceed. Environment-specific branch policies. In a mature DevSecOps setup, there are usually multiple environments: development, staging or pre-production, and production. Each environment corresponds to a branch or a set of branches, and each should have policies calibrated to its sensitivity. The development environment branch may have lighter policies. Automated tests are required, but perhaps only one reviewer is needed. The production branch must have the strictest policies: multiple reviewers required, all security scans must pass, Force pushes forbidden, deletion forbidden, and only authorized personnel can approve merges. This graduated approach reflects the actual risk. A bug that reaches the development environment is annoying but manageable. A vulnerability that reaches production can cause a security breach affecting real users and real data. Summary of key rules to remember. To consolidate what has been covered in this chapter, here are the essential secure branch policy rules. Always protect the main branch and any branch that triggers production deployments. Require pull requests for all changes. Forbid direct pushes even for administrators. Require at least one reviewer, 2 or more for critical branches, who is not the author. Enable stale review dismissal so that approvals cannot be reused after new commits are pushed. Require all automated security and functional pipeline checks to pass before merging. Forbid force pushes to protected branches to preserve audit trail integrity. Forbid deletion of critical branches. Use code owners to ensure security-sensitive files are always reviewed by the right experts. Apply stricter policies to branches closer to production. These rules work together as a system. Removing any one of them creates a gap that can be exploited accidentally or deliberately. The goal is to make the pipeline structurally resilient. Security is not dependent on any individual's good intentions but is enforced by the system itself. This is the practical meaning of DevSecOps applied at the level of version control and branch management.